All right. We are live. Waiting for the Instagram stream to go live here in a second.
Okay.
There we go. Cool. Kicking off episode 4 of the ZKDL camp. What's up, Jesse?
What's up, man? No intro. It's kind of it's like
strange.
I'm used to I'm used to
we don't
having
have
some sort of
I guess
intro.
we should make we can do the hashing out one. I need to upload the video here. We can do that one.
Okay.
But last time we left off talking about congruence. I think we went through this like lemma 3.31 key congruence relation properties.
Mm-hmm.
Just start with a congruence class or residues of K. You haven't seen these before. We're going through the zero knowledge, distributed labs lecture notes. Introduction to zero knowledge. And we're in the kind of math overview part of the book, which is, kind of required math to get to the actual zero knowledge part of things. And now we are currently in modular arithmetic. And after this, we'll do, I think it's Euler's theorem, or no, Chinese remainder theorem is next. And then Euler's theorem. So we're actually just reading through the book, going through examples, trying to explain it to ourselves. If you're watching this, you're learning with us. You want to go ahead and start reading definition 3.32?
Kind of want to, because it's been 2 weeks since we last did this, and I'm not gonna lie, like I stopped looking at this because I was working on the pilot installer.
Yeah.
So, like, can you rehash for me what was the pretext of what we're about to go into?
I mean, we're doing modular arithmetic, so like, how do you do? Like, first off, what is modular? What is modular arithmetic? What does it mean to say like 5 mod 3 and all the different parts of that? What the remainders are, and stuff like this, and then some of the more mathy stuff on how you can move things around. Find what the concept of congruence.
What is the concept of congruence?
How you can move from like regular arithmetic to modular arithmetic and back and forth to try and do some things. I think the main point of all of this was like we're finding some good kind of math and shortcuts that once we get to designing circuits or looking at what it means to make a zero knowledge circuit, how to then make the math work out such that you're in the end, the circuit has the least amount of operations so that it's efficient.
Okay.
That's the way that's my intuition on what we're doing here, on like why we're learning about these various math concepts and like how to move and do arithmetic on these things.
That tracks. I just reread 3.5. Yeah. And then to your point, it's all about optimizing the circuits at the end is all this is for.
Yeah. After this is going to be abstract algebra. So I think that even goes a little bit deeper.
What about congruence classes? Like why
I don't know. We haven't gotten there yet.
Okay. Well, that was previous. Well, wait, hold on. Oh, we're on 3.
We didn't do congruence classes. We just talked about what congruence is.
Okay.
This is like, I guess, like a set. It's like for any given. Right, so reading it, the congruence class are residues of K modulo n. So if you say like this modulo n is defined as the set, it's a set. K plus n of z, or n times z, which is integers?
Integers. Yeah. Yep.
Is equal to K plus n of t. What is that? As a divisor of t?
Is that what it is?
Yeah.
Okay.
Sometimes denoted as the set of K or the set of K sub n. So for example, the congruence classes of the set of 0 sub n, 1 sub 2 modulo 2 are respectively even and odd numbers. So I guess the sub is the modulo, right? So the set of 0 sub 2 is even numbers. I guess that means it's like these are all of the things that are mod 2, like evenly mod 2. And then, or there's no remainder, right? So like, if I look at that, and if I take a number mod 2, all of the numbers that have no remainder is that set, right?
So I'm looking at the definition above, and k is 0, right? In the first example in 3.14, k is 0, so it's just 0 plus, and then some, I guess
Factor.
the n is a modulus, right? N is modulo 2 in the example, so it's 2 times, and then any integer.
No, it's going to be n times 2. 2 is a.
Okay. Wait. And no. Look at it. It's n is 2, no? And then z is the increment.
Yeah, I guess so. N is 2. Yeah.
Yeah. And then the next part, in turn, the congruence class 3 sub 5 modulo 5. Oh, why do they have to repeat that?
I don't know.
Why would you? My understanding based on the example above is when you put in the square brackets 3, that is your
modulo,
k, and then the subscript.
The mod,
yeah. Well, no, the subscript is the mod. No,
that's what I thought. But why would you have to say modulo 5?
Exactly. Yeah, it sounds redundant. Is the set of numbers that give the remainder 3 when divided by 5. Huh. Okay. So
that's
then
an easier way to say it. I think that example, like saying it out that way makes it more intuitive for me. Like, set of numbers that give the remainder 3 when divided by 5, right?
But I wonder if that was intentional, that modulo 5 after writing square brackets 3 sub 5.
I don't know.
All right. Definition 3.33. The complete residue system modulo n, or residue ring, is a set of integers where every integer is congruent to a unique member of the set modulo n, usually denoted as z sub n is equal to open curly braces 0, 1, 2, all the way to n minus 1. In more formal literature, the set is often denoted as z divided by n times z is equal to curly brace, open curly brace, square bracket. Yeah. So it's a set of congruence classes, I guess, is how you would read that.
Complete residue system modulo n. Residue ring.
What was it called when you have like
every integer
when you have a field
congruent to a unique member of the set modulo n. What did you say?
I remember when you have a specific field and you find a generator that is the exponent of the field to the power of that. Is it the generator that is multiplicatively divisible into that field?
I don't know.
Okay.
I never spent much time in modular arithmetic. All the math that I've
done.
didn't
either. I didn't either.
I don't know, like,
honestly,
the language of it. Like, I have an intuition on how modular, how it works.
Yeah.
I don't have the experience doing it and playing with it and
neither do I.
Nuances and intricacies of it.
Yeah,
maybe we'll get there.
Hopefully, I just want to get to some hands-on example. That's
the end of this episode should be a bunch of hands-on examples.
Yeah, that'd be nice.
Because the end of the chapter they have exercises, so we'll just try to run through the exercises and figure it out.
Yeah. Okay. Example 3.15. Z sub 5 is a complete residue system modulo 5 and consists of the following elements. Z sub 5 is equal to open curly brace 0, 1, 2, 3, 4. Sometimes the formal literature defines z divided by 5 times z to be the set of congruence classes modulo 5. Okay. So z divided by 5 times z is equal to open curly brace. It's a set of sets, like you were saying earlier, where the first set is 5k. And what does the colon mean again?
Parameterized by.
5k is parameterized by k belonging to the set of integers z. And so it looks like the thing that we're incrementing here is by the elements within the original residue system. So it's going to be 5k plus n, where n is 0, and then 5k plus 1, 5k plus 2. Is that how I'm supposed to read that? Or
Yeah, I think so. That's what it looks
okay.
like. It's like the set is like the first, if you look at the set 0, 1, 2, 3, 4,
Yeah.
and then the complete residue system, it's 5k plus 0, which is just 5k, and then the ... to 5k plus 4, which is the end of the set. So like, sure.
Do you have any intuition for what this structure actually is doing for us? Okay, me neither. Okay. The aforementioned, so like I'm just going to keep reading, and then hopefully something will click. Okay.
Yeah.
The aforementioned lemmas and definitions describe the properties of addition, subtraction, and multiplication. But what about division? To define the division, if such operation is valid at all, we need to consider the so-called modular multiplicative inverse, which is usually denoted as a to the -1 mod n, similarly to real or rational numbers. Definition 3.34, a modular multiplicative inverse of an integer a modulo n is such an integer a to the -1 that satisfies a times a to the -1 is congruent to a to the -1 times a is congruent to 1 mod n. Example 3.16, let us find the modular multiplicative inverse of a equals 3 modulo n is equal to 7. We need to find such a, I'm just going to say a inverse. Yeah, I'm just going to say a inverse because that makes so much more sense to me. A inverse that satisfies 3 times a inverse is congruent to 1 mod 7.
Normally you'd say that as dot.
Oh, 3. Yeah. Sorry. Yeah, it's a dot product. Yeah. 3 dot a inverse is congruent to 1 mod 7. By simple brute force, we find that 3.5 is congruent to 1 mod 7. Thus, inverse of 3 is equal to 5. Huh. I would need to do that out. I don't know if you're like me, but like when I'm reading, I only can focus on reading. It's hard for me
to none of that really meant anything to me.
Yeah. Let us find the modular multiplicative inverse of a equals 3 modulo n equals 7.
You want to get on the same Miro board as me?
Sure.
You can write as I write?
Yeah. That works.
I'll send you the link to it real quick.
Okay.
Get rid of this so I don't look to it later. I'll set a password later.
Just let me know where you put the link.
It's in Discord.
Okay.
Joshua. I don't know what that is. Sorry, Josh, I don't know what that is. Talking about your knowledge right now. Someone on Instagram asked about our impressions or thoughts on Coin Mafia.
Oh, I don't know what that is.
I don't know what that is. Never heard of it. This ain't the episode to look into it.
This is loading really slow. The Miro board. Yeah.
It's fine on my end. Works on my machine.
Works for me. Oh my god. Load.
You get too many computers going on.
No, it's probably, maybe I should just open it with Chrome instead. Brave always has like issues.
Let's try to run this example out.
There it goes. Yeah. All right.
So find modular multiplicative inverse of a equals 3 mod n equals 7. You define such that a inverse satisfies 3. So a minus 1 satisfies 3 dot A inverse congruent to 1 mod 7 by simple brute force. Find that 3 times 5 is congruent to 1. 3.5 is congruent to 1 mod 7. What? How is 3.5 congruent to 1 mod 7? It's like it's 15. 3.5. So it's like if I'm like thinking this out, 3.5 is congruent to 1 mod 7. So 3.5.
I'm gonna get the mirror link to work on my tablet.
Mod 7 gives you 1, right, as a remainder. That's true. That's mod 7 here. (15 mod 7) because like 7 times 2 is 14, so you get a remainder of 1. So I guess that means 15 mod 7 is congruent to 1 mod 7 because they both have the remainder 1. So I don't know how that
Did
goes.
you do the dot product of 3 and 5? I forgot.
Yeah, it's just the 3 times 5 is 15. So like 15 mod 7 gives you a remainder of 1.
Oh, wait. So it's not a. What's it?
For scalars,
Dot product of scalars is just multiplication.
Yeah.
Dude.
Yeah.
Got it. Yeah, that makes sense. So 15
like, I don't understand what the thus means, right? It's like, how do we get to like 3 inverse equals 5? How does that work? Because 3 times 5. Okay.
What is?
I see here. So if I look at here, let me change my color, my ink. If I look here, right, I'm plugging in, just like plugging in, right? So like what number?
I'm playing catch up.
Times
Walk
3.
me through what you did. Now I'm looking
well, like
at
I was just reading the example. The example says by simple brute force, we find that 3 times 5 is congruent to 1 mod 7. So I just multiplied out 3 times 5 gives you 15. Took the modular, took mod 7,
and then you got 1 as a remainder.
Right?
Yeah.
So basically, it's saying like, if I look here, what number, what times 3 is going to give me a remainder of 1 mod 7? So what times 3 mod 7 has a remainder of 1? 3 times 5 is equal to 15. Mod 7 gives you a remainder of 1. So by like brute force, the A inverse for this, A equals 3 mod n equals 7. Inverse of A is equal to 5 because it fits into this. So I think by definition, you're always looking for the thing that is 1 mod.
The notation is fucky because I get what they're saying because they're putting it 3 inverse of 3 is equal to 5, but like when they write out that statement,
so if I look
as it stands alone, it makes zero fucking sense.
The definition is like, look at the definition. When you're looking to find the inverse, is what A times A inverse gives you is congruent to 1 mod n, right?
Yeah.
So they give you A and n.
But A is 3, right? So like
A
for
is
instance,
3. So what times 3 gives you 1 mod 7? Answer is 5 because 5 times 3 is 15.
But
15
do
mod
you see
7.
how
15 mod.
the definition is A times A inverse? It should
Yeah.
be A times B inverse, where B is equal to 5 and A is equal to 3.
No,
You know,
A
because like
times
if you're using
because you're looking, you're one. It's an identity, right? So it's like when you do. This is the identity for modular arithmetic. What is the negation?
like A times A inverse is going to be 1. Like I get that, but
1 mod whatever modulo we have, right? Because we're doing it like we're doing this as modular arithmetic, so it's always going to be.
this is
like
this is all I
working around the
mean.
clock.
Let me sketch out what I mean on your Miro board on my tablet.
Yeah, sure.
There's my little doodle thing in there. Oh no, it switches.
So like if I draw the clock here from what we used previously.
No, I have more of like a beef with the way that it's structured. Like for instance, definition. So like you see what I'm writing here, def 3.34, right? The definition is A times A inverse is congruent to A inverse times A is congruent to 1 mod n.
Yeah.
But in the example they're giving you, so A equals 3 modulo, I'll write it out fine, n is equal to 7. So like you said, right, you just basically A equals 3, n is equal to 7. But all I'm saying is like for, okay, and then I'll write it out. So 3 times A inverse is congruent to 1 mod 7. All I'm beefing over is that in this format, sorry, let me undo that. Can I not hit the undo button?
Yeah.
There you go. I'm going to use a different color so it really stands out what I'm talking about. So like essentially they're taking this, right? That's this structure right here, right?
Yeah. Yeah.
All I'm beefing over is that the way that I know that, you know, A times A inverse is equal to 1. That's the identity. The dot product of the
but
identity.
in modular, there's going to be 1 mod, whatever the modular is.
Yeah. But like, what all I'm saying is like, in this case, like, the answer was when they wrote it out, they said 3 inverse of 3 is equal to 5. It's just it reads a little bit weird because
it does,
like, because this is 5.
That's 5,
but
yes.
it's actually not even the inverse. It's just 5.
It's just 5.
Yeah. But
the inverse of the 3 is like 3 to the negative. Like inverse of 3 modulo 7 is going to be 5. I don't know what the right words are to say this. Write it out.
Yeah.
Like
exactly.
that just looks weird. But like you always have to keep in mind it's like modular arithmetic. So like this, like the notation doesn't sit well for intuition.
Right. Because like if they're using A's here, right, it should be fucking 3. It should be like it like that. You know what I mean?
It just doesn't make any. That doesn't help.
Which doesn't make sense. Exactly. It doesn't help.
Either.
That's what I'm saying. Like that's what I'm saying. It doesn't help.
I was trying to look
at
it from a clock perspective.
This.
Like
That's why I was asking. Like this, they should have made this B or something. You know?
Yeah.
I mean, I get like 15 mod 7 is going to be, you know, you go around the clock twice and then you have 1 left over. Like, I get that. I'm just beefing over the notation that they're using because it's, I don't know. Just, I would have used not A times A inverse. I would have used A times B inverse, but that, like you're saying, it's not the identity matrix. So it's just, there's something weird here with the notation that doesn't make sense to me, but I get what they're trying to do.
Yeah, the intuition of inverse in modular systems isn't straightforward.
I mean, also writing it like that expression is false. like three in like inverse of 3 is equal to 5, like that expression is not an appropriate way of expressing what they're trying to say. I don't think, is it?
I would imagine it should be. I'd have to look at a different book. Maybe someone in the audience can tell us. We could bring in one of the GK guys from the IFT on like.
That would be nice.
Hey, Balaj.
Like, just tell us if we're retarded, or like tell me if I'm retarded to.
Yeah, tell Balaj, make us feel stupid about this and make us understand it better.
Okay, cool. We can move on.
Yep. All right. So we got that kind of remark. The inverse, if exists, behaves similarly to the usual inverse over rations or reals. For example, a squared inverse is equal to a inverse squared. Okay, which means we can first find the inverse, then square the value, or vice versa. So whichever process makes sense, you can do it.
Yeah.
Question then is, when does the number have the inverse? Consider the following theorem. The modular multiplicative inverse, A inverse mod n, exists and if and only if the greatest common denominator of A and n is 1. Okay. Makes sense.
So if it's prime, then it's got an inverse.
If you can do prime factorization to it, then...
Yeah.
Okay. So based on the extended Euclidean algorithm 1, definition 3.5, we build the algorithm that can verify an existence and find the inverse. So here's the algorithm for doing this. Maybe we can write this out here in a little bit when we get to the exercises. So extended greatest common denominator, need that in order to do the inverse. So if you're trying to find the inverse of A and N, I'm looking here, right? Trying to find the inverse of A and N, you first find the extended greatest common denominator of those two things. If that is not equal to 1, you raise a value error. Otherwise, you give U, which is what we have up there in the previous. So it doesn't exist.
I never did this out on it by hand.
Yeah, it's basically saying like if the greatest common denominator isn't 1, then it doesn't exist.
Yeah.
If it is 1, then return U. So
that makes sense.
And they're using, it looks like, one of the previous, the extended Euclidean algorithm here.
It'd be good to take snippets.
Things.
Yeah, take snippets of the extended Euclidean algorithm above as it's explained, and then like slap it into Miro, and then take this and then slap this into Miro as well. Like just a snippet.
I imagine we'll do that in the exercises.
Okay.
Why don't we just get through this and then start trying to power through exercises, just see how we do.
Yeah.
Let us verify manually that 12 inverse modulo 17 was found correctly. Consider the following example. Let us find the modular multiplicative inverse of A equals 12 modulo n equals 17. First of all, we need to verify that the inverse exists at all. In other words, whether the greatest common denominator of 12 and 17 is equal to 1. So they go through that algorithm to find that, yes, it does exist because the greatest common denominator is 1. That's the thing we did last time of the extended Euclidean algorithm.
Mm-hmm.
I bet that's a really cool visual representation of what the extended Euclidean algorithm is, right?
Yeah.
You can map that to something visual that I think would probably provide some pretty good intuition.
Yeah.
So you can see how it progresses down.
Mm-hmm.
Because you can take them like 17 modulo 12 gives you a remainder of 5. Then you take
12 and you bought modulo 2. Modulo
12 equals 5. Modulo 5 gives you a remainder of 2. 5 modulo 2 gives you a remainder of 1. And then you're done.
2 modulo
0,
is
you
0.
take it. 1 is the greatest common denominator.
Yeah.
That's the way that extended algorithm works. But like, I bet there's a really cool graphic visualization just to make sure that it gets
like the bubble sort, like visualizations. Have you ever seen those?
Yeah.
And there's like noises like
yeah. It's cool heavy existence, which means that you can find an inverse. They've previously used Bayes coefficients, but in this case, we'll show you another method. Let us iteratively go backwards from equation 3. The fuck is equation 3?
5. This one right here. 5 equals 2 times 2 plus 1.
Is that the one they're talking about? Okay, yeah.
I don't know. And then they're moving 1 on the other side, so it's 5 minus 2
the rest
times 2.
Steps, so.
1. Yeah, so they're just flipping it over.
Yeah.
And then what do they do?
1 equals 5 minus 2 times 2 equal to 5 equals 5 minus 2. So they just plug the previous step into that part. And so combining, we have 5 times the entity 17 minus 12 and 1. As you can see, we have found the Basel coefficients of the greatest common denominator of 12 and 17 equal to 5 times 17 minus 7. I guess a different way of getting to the Basel coefficients by working backwards. Therefore, the inverse is -7 because like plugging in, so the U is the Basel coefficient. So like U is minus -7. If you look at the Basel coefficient definition, if like the Basel coefficients are 5 and -7. And by definition, because you do this part, like U ends up becoming the inverse of 5. Yeah.
Interesting.
Okay. We'll have to confirm that. Note that the complexity of this algorithm is the same for algorithm 1. There you go. That's tying it back into bit operations for usefulness later when making things. In real applications, typically n is larger than a. So the complexity is simplified to O log squared n. Okay. The multiplicative group of integers modulo n, denoted z sub n of x, or to the x, is the set of natural numbers that are co-prime to n and less than n. In other words, a within the natural numbers parameterized by the greatest common denominator of a and n equals 1. So only the numbers that are co-prime.
Co-prime to n and less than n.
Yeah.
Interesting. Okay.
So this,
what does that do for us?
Since all naturals less than 11 shortens. Are co-prime to 11, since 11 is prime. However, for 12, it's smaller since the integers 2, 3, 4, 6, 8, 9, 10 are not co-prime with 12.
Yeah, I see. So it's just shorthand. So they're just going to start writing Z subscript.
It's a set of co-prime numbers of 11.
Yeah. They're just going to use that format. Z
multiplicative
to the
group
power
of
of X.
One of those are useful for, but I bet that comes into play pretty heavily when doing optimizations.
Z, how do you read this? ZX sub n? Is that how we're going to read it? Z to the X sub n?
I don't know. How would you say that?
Fundamental object in number theory plays a crucial role in cryptography, forming the basis or basis for almost every cryptographic primitive. The structure of the group Z to the X sub n has a crucial meaning. It has deep connections with the algebraic structures. Even the number of elements of Z sub n, Z to the X sub n, has a special name which we define below. Definition 3.37. Euler's totient function. Is that phi?
Phi.
Phi of n is the cardinality of the multiplication group of integers z to the x sub n. In other words, phi of n is equal to absolute value of z to the x sub n.
Cardinality. Okay. So that's like...
Yeah, what is cardinality?
Cardinality is usually a increasing order.
Okay.
That's why it's absolute value. It's usually like denotes the an order of something. It's like increased complexity. So like dimensionality, right, would be kind of like a cardinality. Like the real numbers have cardinality 3. Or like real space is like cardinality 3 because it's r to the third.
Oh, okay. I see what you're saying. Oh, okay. I remember. This is like in XYZ space, cardinality 3.
Yeah.
Yeah, I got you. I remember. It's coming back. All right.
The alternative Euler's totient function interpretation is the following. Phi of n counts all coprime integers with n in range 1 to n. Remarkably, phi of n has a lot of curious properties which we specify below. Let's see how remarkable this is. Lemma, Euler's totient function properties. Phi of 1 is 1. Phi of p is the p minus 1, where p is prime. Okay, that's interesting. So any prime number, the phi is 1 minus the prime number. Just like you looked at the phi of 11, it was 10. Okay. Phi of p and q is, okay, that's interesting. That makes sense, though. If okay, I heard in, there's a recent Lex Friedman podcast where he interviews a guy who is a specialist in set theory.
Okay.
Really interesting if you like the philosophy of math.
Yeah.
Can
you sum up what that means in a nutshell? Like, what is the philosophy of math in a nutshell?
Like, for instance, like one of the things that he said, which is what I was going to get to, is like they consider primes as the atoms of math.
Okay.
Right? They're like the things everything's built from.
Okay.
So like if you think about all of math, primes are like the atomic unit of math.
Okay.
Because everything can be prime factorization. Every number can be a decomposition of primes.
It's just a matter of
they're
time.
the basis functions of all of math. And I thought, like, if you think about that as the abstract math space and how it relates to, reality.
Yeah.
And like,
but that's only for real numbers. It doesn't consider imaginary numbers, right?
No, it does. Imaginary numbers are still numbers. Are just it's a two-plane.
You can factor a complex number.
Yeah.
Into primes.
I mean, it would still have to lie onto the complex plane, so it'd be a factor of primes plus or minus a factor of primes, I times I.
Huh. Okay.
It's like saying like you can't factor, maybe I'm wrong here, but like you can't factor x and y into a single prime number, but you can do x and y into two prime numbers of the coordinate set.
Yeah, you're just postulating that. You don't know that for sure, right?
Yeah, that's my intuition.
Okay. Maybe it's right.
There's not I don't think there's a mapping of the complex plane to just prime numbers. That's like that gets into like infinite sets and stuff. So like that's maybe like beyond what we need to talk about here. Anyway, with these properties, we can derive a general formula for Euler's totient theorem function known as the prime factorization of n. Okay. For any number, n equal to prime 1, alpha 1, general formula Euler's totient function is phi of n is equal to the product from I to t, p of I to alpha I minus p of I.
What's the difference? Let me ask you this. Like, what's the difference between a lemma, a corollary, a
corollary is like a different way of saying the same thing. The way I've always understood it.
The same as a lemma? Or
a lemma is like it follows that.
Okay.
Right?
I don't know. I always like
the lemma here is like here's like a lemma is like given this definition, it follows that these things are true.
Then what's a theorem? I'm just gonna go through all this stuff that I
theorem is like a true statement, like
it's been proved true. There's no
proof. There's a proof.
There's no counter. But it's not like, you know how like I guess in physics you have like laws, but laws are not necessarily like some laws are not laws. What was it? How did that go?
Theory is usually something that has been backed by a tremendous amount of evidence.
Okay.
And it has like it is a almost like a mathematical construction that explains some phenomenon that is backed by a tremendous amount of evidence from experiment, and then has predictive powers that allow you to, following the theory, and given this theory to be true, we predict this thing to happen that say hasn't had an experiment yet. So you can go out and do new experiments that then validate that theory. It's like, I have a hypothesis that based on this theory, I can do this thing that hasn't been done before.
My question is less about, it's more about the hierarchical organization of terms in math that parallels that.
Yeah, I don't know.
How does that go?
It's a good question.
Like, is it theorems, then lemmas, then corollaries? And like, it's like theorems are the basis of everything. Like, they're the laws or whatever.
Like a theorem, in my opinion, is like given a framework of axioms for in math. So axioms are like, these things were just taken to be true. There's no proof of these things. They're taken to be true. And then subject to logic on how we can put these things together using the axioms, we can prove that this statement is now true, right? And that's the theorem. The theorem is like, we have proven this statement to be true from the set of axioms. And that's and logic and pure logic. It feels like a corollary is like an alternative explanation of the exact same theorem.
Okay.
And then lemmas are like, given this theory to be true, here is a number of other true statements that are derived from it.
Oh yeah. So it goes axiom, then theorem, then lemma, then corollary. That's apparently how it goes. So like you said, axioms are self-evident truths assumed without proof. Theorem is a major proven statement. Lemma is a minor proven result used to help prove a larger theorem, a quote unquote helping theorem. A corollary is a direct, easy consequence of an already proven theorem. The key difference lies in their roles. Axioms are starting points, theorems are major findings, lemmas are stepping stones, and corollaries are quick follow-ups. I like that.
Okay, nice.
I don't know.
Clip that. That's useful.
Interesting. Yeah. Okay,
all right,
we can get back to it.
Cool. So Chinese remainder theorem. We actually might have time to get some exercises. We're 30 minutes in. We're 40 minutes in. I guess we started early. Whatever. The Chinese remainder theorem is a fundamental result in number theory that provides an efficient method for solving congruent systems. It allows one to decompose a complex problem with large integers into several simpler problems with smaller modules. This decomposition reduces the required computational complexity, there you go, especially when working with large numbers. It is widely used in areas such as modular arithmetic, cryptography, and algorithmic number theory. So that's something that's, I think, generally people should look for when solving problems, is the ability to decompose that problem into smaller problems that you can then solve in, like one at a time. That's like always the strategy when trying to solve problems that seem really hard, is how do I deconstruct this problem into smaller problems, solve those independently, and then recombine them to get to the larger problem.
So people will bitch at you for vibe coding things because it's way more code than necessary, more often than not.
Yeah, I guess you're doing it wrong.
And it's not. Yeah, I mean, you're just telling the computer, hey, make it so.
Yeah, but it's also like, if you can tell the computer, to make it so subject to these.
Yeah, of course. Then you get hopefully you get a better
answer.
Output. Yeah.
Other than like, hey man, like, instead of saying like, make me this thing.
That's why pre-planning is
make me this thing using React, so it doesn't reinvent React in the process of making it.
Yeah, exactly. Exactly.
Here's an example. Did it even show them? Oh, it didn't. Did I miss that? What happened here? Suppose there's a following system. X congruent to x1, x congruent to x2, mod n2, x congruent to xt, mod nt. Okay, where n sub 1 to n sub t are pairwise coprimes, and x1 to xt are fixed numbers. Okay. Then this system has a unique solution modulo n equal to the product of n1 to nt. In fact, we can easily find such a solution. Let n sub I equal to n divided by ni. I think there's a way to say that, which I forgot previously. since n1 to nt are pairwise coprime, we have greatest common denominator of ni and little ni equal to 1 for each I. So by the extended Euclidean algorithm, there exists an ai such that we just did that one. Thus, the solution is given by this linear combination of these factors. So that's interesting. That then is the decomposition of. That's interesting. This expression provides the unique solution modulo n, where n, capital N. Besides using this idea, we could write an efficient algorithm to compute x naught iteratively. So like this allows you to decompose these, like given these things are true, you can decompose this large problem into a linear combination of smaller problems and then solve each of those ones separately. Like the A1 capital N sum 1, like this part here is a part of the decomposition. Mm-hmm. And so when I say linear combination, I mean this part.
Yeah, it's just adding the products. Yeah, of each step, so, like A1, N1, X1 plus A2.
And looking at this, so where
shouldn't there be a parentheses around the entirety of this thing before the mod n, or does that assumed or applied?
It's applied. I think at the very end of the statement when you do mod n, it's just like this whole system mod n.
Okay.
Okay, so first of all, we find n is equal to, so we define capital N, 5 times 7 times 11, which is equal to 385, and we compute n sub I. Capital N sub 1 is equal to 7 times 11. N sub 2 is equal to 5 times 11. Okay, and the last one should be 5 and n sub 3, 5 and 7. So you take the product of the other two. For any given n sub I, it's the product of the other two, right? You see this?
I'm reading along behind you. So first of all, we find n is equal to 5 times 7 times 11 is equal to 385. So that is your
capital N.
Your ATNTXT format, I suppose.
Well, what the fuck did I do? How did I do that? That's interesting.
Then we compute n sub I. N1, so that's the first term. So 7. So where did they 7?
I can do that.
7 times 11. 7 times 11. N is equal to 5. Let's see. So we have that. N is equal to N1, N2, NT. N1, N2, NT. So 7, 5, 7, 11. N1. Why are they pulling from N2 for N1? 7 times 11?
It's the product of the other two coprimes.
Oh, I see. So, okay. I see. Okay. 5 times, N2 is 5 times 11, and then N3 is 5 times 7. Okay. Simplify calculations. We give inverse for granted. A1 equals 3, A2 equals 6, A3 equals 6. To simplify the calculations, we give inverses for granted.
Just saying, like, we're going to give you, like, just
to give you those.
Thing, we're going to give you the inverses.
Yeah. Okay, so 3, 6, 6. Solution is then given by x sub 0 is equal to 3 times the n1, so 77 times 1, x. Which is x equal, x can to 1 plus.
Right, yeah.
Then the next one, 6 times 55 times 2. Okay, I get it. Congruent to 1521, congruent to 81 mod 385. How did they get the 81? They just solved it? No. Where's the 81?
How did you get to what? The 81?
Yeah. Where's that one coming from?
It's just like, I think it's just solve.
They just solve it down. Okay. Okay. Yeah. So it's like 3 here. Let's just
So it's going to
about
be
calculator.
like 81
3
is
times
probably
70.
what due to a 1521
Huh?
mod 385 should be 81.
15, 21
Mod 385.
385.
That's probably going to give you 81 as a remainder.
Oh no, I'm not using this calculator correctly. 1521 times mod.
What's what? Yeah, let's see here. Pull up my terminal.
Nope. Okay. So you can't write it how it looks. Oh no, 1521 divided by mod 85.
1521
No,
mod.
I think you just got to do 81 mod 3.
This is 3.
85. Wait, what?
Is it a remainder? Yeah, we need a remainder. So I don't know. So what's another remainder?
Use Wolfram.
Python.
Wolfram.
1521 minus 3 times 385. 366. So that's not right.
Oh, you just use triple equals. Okay.
Let's get to that one then.
Yeah, I'm about to do it.
I'm just going to move on to Euler's theorem.
No, not yet. Solve for x.
Where are you? Where are you doing this?
Wolfram on a
Okay.
on a browser. Yeah.
Okay.
Yeah. I'm just writing the expression 1521 is congruent to 81 mod 385, where I'm just leaving 81 as x and saying solve. But
Okay.
that's not doing it. So not entirely sure. Yeah, if you do, what did you get as a result? Because I'm getting 366 because I'm just throwing in
as well as a remainder.
Yeah, this doesn't make sense. Hold on, we're doing this wrong. Where is my?
We just multiplied it all out. Like 3 times 77. Here we go. Let's do this. 3 times 77. Where'd it go? Times 1 plus 55 times 6 times 2 plus 6 times 35 times 3. 1521. Okay. How is 1521 congruent to 81 mod 385? $385 is the capital N. So we have, looking at 1521 congruent to, just call it A mod N. It doesn't look this already. Let me see. $385 there something we've learned earlier about this? I have to write down all the definitions for these things in like a cheat sheet to see like
Yeah.
you know?
Yep. Yep.
Or there's something here we're missing that we previously learned. It's like, oh, A is this because of this. That 81 is that because of.
I just threw it in ChatGPT because we keep getting 366. Okay, yeah. I mean, even ChatGPT is like this. It's 366. Hold on. If you try 81, the difference.
Just like take the whole fucking thing out and then like. Let me take a picture of it and put it in.
That's exactly what I did. I took a picture of it.
Example.
The whole the bottom of it, and I'll put the whole example in this time. I was just like, show me how you get 81. It was like, it's 366. Hold on, show me how you get 81 in this example.
Did we find a problem?
Probably not. We're just, like I said, the notation in this book is a little bit off.
Yeah. This is why people don't like math.
Yeah.
Let's just move on. Let's get to the fucking examples.
All right, that's fine.
All right. Euler's theorem. Now we are ready to introduce one of the fundamental results in number theory. Okay, now we've built up to this. Euler's theorem was discovered by the mathematician Leonhard Euler as a generalization of Fermat's last little theorem. Why is it so important? Euler's theorem is a key result in number theory in cryptographic applications such as RSA encryption and so on. Essentially, it helps in understanding the structure of the multiplicative group of integers, modulo n, and gives a foundation for other important results in number theory. Besides, it provides the simplification of large exponents in modular arithmetic. The theorem states a to the phi of n is congruent to 1 mod n for any a that exists within, what was that, the congruent set, or like?
It's just notation. I don't know if it's
ZX sub n was like, what's the name of that? Like
yeah, here I can
congruent
query
set.
Yeah,
so
it's a set of here I can
scrolling.
I'm gonna ask ChatGPT for alternative ways of saying that.
The multiplicative group of integers was the ZX sub n.
Yeah. Multiplicative group of integers. Yeah, 3.36. I see.
So like I see in my head, I see like the multiplicative group of integers as the basis functions of a given modulus.
That seems fair.
That feels like a right thing to me, right? Given a field over like when I think of modular arithmetic, mod n is the field in which you're operating, and the basis functions of that field is this set, right, of multiplicative integers. Does that make sense? It makes sense in my head. I don't know if it makes sense to you.
I get what you're saying. I just don't know if that's how it's gonna be. If that's how it's gonna.
Yeah, I'm very curious to see if that intuition is right, because I'm trying to I always explain it in terms of linear algebra. Maybe when we get to linear algebra, it'll make these connections for us.
How do I read this? Also, by the way, ChatGPT said you don't get 81 from that computation with modulus 385. It's a mistake in the example. Here's the correct reduction step by step. So
yeah, finding shit in the book.
I don't know that it's. I assume
I'm going to take this problem to someone who knows this stuff and see if we're right.
Tell me how Balazs interprets their notation, because I have a feeling it's not a problem of the math. It's the way that they intend to convey a thing, and it's written wrong.
Yeah, I'm gonna take this to a group of people and get an explanation from them. We'll come back to it next episode.
That sounds good. That sounds good.
Or maybe we can have them on next episode and like, hey, explain this to us, because it's either wrong or we're really not getting it. It's like
yeah.
All right. So lemma. Suppose a within this set of multiplicative integers, denote that a times it. So a is the set of ax parameterized by x within them. Then z sub n of x equals to a. Oh, wow. Element-wise multiplication by a permutes the element.
So
That's a
they read.
permutation. So, okay. If you multiply the multiplicative set, it does a permutation on the set. It's still the same set. It's just permuted.
I mean, that makes sense. Why? Like, does permutation mean something different other than changing it to you?
It's
Like,
more of a rotation. So permutation is more like a rotation.
Okay.
So it's the same thing viewed in a different angle. Right?
I see. So when you're multiplying all these, all these subgroups, you're rotating the numbers within the field.
Yeah.
I get where you're going.
Our statement is equivalent to claiming that the function f goes to a, okay, defined as f of x is equal to a of x mod n, is a bijection. To show this, we need to prove the following three statements. Correctness is obvious since ax is in a.
Are you? Let me just interrupt. Like, for a visual, like a mental visual, like you're viewing it like a bunch of clocks getting multiplied by some factor, and all the clock hands are rotating or something like that, right?
Yeah, kind of. That's how I'm kind of intuitively trying to view this.
Yeah, that's what I get where you're going.
We need to prove that if f of x of 1 equal to fx2, then x1 is equal to x2, which exists within the set. From the function definitions, we have ax sub 1 congruent to ax sub 2 mod n. By the following definition, 3.31, you can cancel a modulo n as a is co-prime to n. Then, okay, surjectivity. I think it's be subjectivity. No, surjectivity.
No, this surjection is a different one.
We need to prove that every element y within this has at least one pre-image inverse f of y. Then the set x is defined as a inverse y mod n. This expression is well defined as a is co-prime to n and has an inverse. Therefore, f is bijective, and thus what we set out to prove in the first place. So we know that this, what we just said. How do we proceed? Cool. Notice from the set equality follows the equality of the products of all elements. Let's write down. Oh, I don't want to say all this.
Yeah, you've been skipping some stuff when you're reading.
Yeah, it's just the way my head works. Are people actually just listening to this word for word?
I don't know. So the product from I equals 1 to phi of n of x sub I is congruent to the product of I'll just read it. The products of a x sub I from I equals 1 to phi of n mod n. How do you read that arrow?
I forget. Like implies.
Implies. Okay, I was just can also be rewritten as.
Okay.
This is like, I don't know.
It follows that. I don't know.
Okay. It looks like it's the same first term. It's a product of x sub I from I equals 1 to phi of n is congruent to, and then there's like a factor extracted out from what looks like the second term, which is, so it's outside of the product. Yeah. So a to the phi of n. So phi of n is an exponent of a times the product of x sub I mod n from I equals 1 to phi of n. Since all x sub I are co-prime to n by definition, we can cancel out the product of all x sub I from both sides, leading to the conclusion of Euler's theorem. Example 3.21, let us consider how Euler's theorem works by computing seemingly scary expression 29 to the power of 202 mod 13. By means of definition 3.41, we have 29 to the phi of n is congruent to 1 mod 13, where phi of 13 is equal to 12. Using this, let us try to simplify the expression. So 29 to the power of 202 mod 13 is congruent to, and then they have algebraic simplification here of 29 to the power of, and so they're expanding the exponent 202 into 12 times 16 plus 10 mod 13. Then they have the first, they can pull out the term 29 to the 12 times 16 as a term that cancels out. So they're just left with 29 to the power of 10 mod 13. And then 29 itself, they simplify that to 3 to the 10 mod 13. There's a lot of
Why does the 29
simplifications here. I don't know how they're doing
cancel
that.
out?
So yeah, I don't know. That's probably in the definition above, and we just didn't grasp that.
No.
And I don't think that's something that you can work by hand.
Yeah, that
you just
step
kind of,
there is the one that I'd like to understand, the canceling out.
That's fair. Let's see. Let's go back up here.
I guess it's like they only care about the remainder in this, right?
Let me.
Like if you
I need to go up to go back down. So, like for instance, the conclusion that they make after the example, they have 3 mod 13. In other words, we significantly reduce the computational complexity by using Euler's theorem. Now let us consider one essential corollary of Euler's theorem, which is used in finite field arithmetic. If P, okay, corollary 3.43, if P is a prime number and A is not divisible by P, then A to the P minus 1 is congruent to 1 mod P. This result is commonly known as Fermat's little theorem. However, to maintain generality, we state the theorem in a more general form below. Okay, so like there's something up here to get that. Let's go back to your question. 29 to the power of 12 times 16. There must have been something up here. Maybe it's this right here. So phi of 13 is equal to 12. It's right here. It's right here.
Where's here?
So in the expression where they
phi
had
of 13 is equal
product
to 12?
of primes. Yeah. So in example 3.21, they have a line that says where phi of 13 is equal to 12. Now, if you go up to the line where it's the product of x sub I from I equals 1 to phi of n. It's like the right half of the expression above. They pull out that a to the phi of n, and that a to the phi of n is 12 there. So that's how they get 29 to the 12. You can cancel that out. But to the 16, I guess that one I'm not sure how they got the 16.
It looks like 12 times 16.
It might be the same. It might be divisible
it's the modulo, to each other. So like 202. Like 12 times 16 is probably 192.
Because they're both even, it's
well 12 times 16 is 192. So like
I think that's what it is.
Because like mod 13, factor it like that. So like if you look at 202 mod 13, you get a remainder of 10.
12. Well, but like think about it this way, like I know it makes sense to you, but like for me, I could just say 29 to the 12. It's just that times 29 to the 12, 16 terms of that. And so each of those,
so like it just rings around the clock, right?
It's just one. Exactly.
So like who cares? We only care about the remainder in this particular thing. We're just able
it all
to
simplifies
to
exponent. 1. Yeah. And that's how they just canceled that out.
Okay, so that's intuitively okay to me, because you're just like, it's like based on this math, we're able to do this in the exponent and then cancel it all out, because like those are. I think I'm going to look at. There's a couple videos from 3 Brown 1 Blue and Welch Labs on Euler's theorem.
Yeah, that would be good to include in the show.
But those are usually around like the main, I guess, instantiation of this is either the I pi is equal to -1.
Yeah,
I want to see it. I want to see that explanation in this language. I'll play around with that off camera probably, because we're almost out of time. The rest of it is kind of just looks like it's just like factoring down.
Yeah. Everything after the first 2 lines is just what we've done before. The 29 to 10 mod 13. It's the same thing.
Yeah.
I imagine 29.
So it's like first reduce the exponent. From there, reduce the.
Well, you have to factor it first. So it's like you're taking 202, which is the exponent, and then trying to factor that into something that's an exponent of 12, right? 12 times something.
Yeah.
And then from there, like the 29 to 3, I actually don't know how they got that one. So what would that be? Oh no, it's just mod 13. So they're just doing
mod
it's 3. It's 26 and it's 3. Yeah, okay, that's fine.
It's like there's like ways in which you can keep reducing things in modular arithmetic, like by only focusing on the thing that's exponentiated or the exponent itself.
Yeah.
Right. They're separable in a way.
Yeah. Yeah.
And that's like the key, I think, insight is that these things are separable, so you can work on them independently.
Yeah.
And then recombine them and then solve that problem.
Yeah.
Because if you look at what happened in the first couple steps, we're basically ignoring the 29. We're only dealing with the 202.
Right.
Mod 13.
Right. Yeah.
And then get rid of those factors. Gives you a smaller
You're just
number.
trying to decrease the really big number into a smaller number that
and like
you can find
all of the
other
steps
patterns.
We've been going through are proved methods for how you're able to do that. Which is interesting.
So you have a theorem that gets proven, and then you're using the theorem to pattern match reduction of the expression from big number to smaller number.
Yeah.
Faster. Yeah. Cool. I don't know, is that a good place to leave off for next time?
No, we have just a tiny bit here. Just a tiny bit here, right? Okay. So let's just run through these corollaries. In other words, we significantly reduce the computational complexity by using the Euler's theorem. Now let us consider one essential corollary of Euler's theorem, which is used in finite field arithmetic. If P is a prime number and A is not divisible by P, then A to the P minus 1 is congruent to 1 mod P. It seems very similar to like we previously said. On like the phi of a prime is like 1 minus the prime.
Yeah.
The multiplicative set, kind of.
Yeah.
If it's prime. Yeah. This result is commonly known as Fermat's little theorem. Fermat's, whatever you say it. However, to maintain generality, we state the theorem in a more general form below. Let P be a prime number. For any integer A, the following holds. A to the P is congruent to A mod P. The proof of Fermat's little theorem is a direct consequence of Euler's theorem. We can consider Euler's theorem as a generalization of Fermat's little theorem. Okay. Moreover, this fact allows to find the modular multiplicative inverse of an integer A modulo prime number faster than using the extended Euclidean algorithm. Corollary, for any integer A and prime number P, the modular multiplicative inverse, A inverse mod P, is A P minus 2 mod P. Interesting. Man, there's got to be some really cool visualizations that help give intuition here. I'm going to go on a deep dive of
Khan Academy has
brown, one blue on this and see if I can
Yeah, they probably have really nice ones.
His visualizations are just beyond.
Yeah.
Because he has an interesting way of like taking it to a different field, explaining in that field, and then making the connection back.
Interesting.
Welch Labs, I think, does a really good job of this too. But those are usually
which one?
Welch Labs. Those are usually in the context of AI and large language models and like that type of thing.
You said Welch Labs?
Yeah, Welch Labs.
Oh, okay.
Okay. Proof. Notice that A dot A P minus 2 is equal to A P minus 1 congruent to 1 mod P from our definition 3.41. Note that computing A P minus 2 mod P requires less than 2 log 2 of P modular operations using the fast exponentiation algorithm. In Python, implementation using built-in POW function looks extremely simple.
It's POW.
POW.
Yeah. I always say POW. It's a power function.
Yeah, power function. So inverse. The inverse of A and P is return. Wow. Okay. Power A, P minus 2 of P.
Yeah.
And then we're in exercises. Maybe we just do all the exercises. We'll figure this stuff out. And we'll just do all the exercises next time, and then we'll actually get into abstract algebra. Probably.
That would be actually really good. Yeah, if next session we try to do all the exercises separately, and then we come together and run through them on camera.
Okay, and explain them to each other.
Yeah, and then the next time we meet, the week after, we can do the next section.
Cool.
Cool.
All right. Good job.
Homework.
That was fun. I don't know.
I enjoy that.
Industry. Later, guys.